So if you choose a large enough prime number, division is practically impossible to do when attempting to reverse point multiplication. And this is the discrete log problem and is the basis of modern cryptography. If it is solved, most of our cryptographic systems will crumble.
In this video, I sat down with Eric Yates, the author of The Seventh Property, to discuss some critical aspects of Bitcoin's operation. Eric discusses the discrete log problem, which illustrates how unbelievably secure cryptography is. We also discuss how mining works, showing you the inputs and the outputs that it takes to mine a block. If you've watched this show before, you've probably heard me make some bold claims that Bitcoin will do X, Y, or Z for the world because it resets the incentive structure for participants of the network. The two examples we explore today are major factors in the establishment of those altered incentives. The craziest part is, these incentives are literally designed by math, linking the digital universe to the physical one. I will also stress that this video is just the start. It's a way to dip your toes into the fascinating world that is cryptography. And don't be afraid, I'm no mathematician or coder. So if I can grasp these equations and concepts, you can too. But before we do that, I want to introduce our sponsors, Stampseed, the Orange Pill app, and Swan. Our partners are businesses and people that we respect and are products that we at Bit Intelligence personally use. You're watching 21 Voices.
I think one of the most fundamental aspects to understand of why Bitcoin is so secure is to understand how secure cryptography is in and of itself. And I'm proud of this section because I spent a good amount of time of work really trying to get my head around how this stuff works. This section is called the discrete log problem, and this is the problem that enables us to use math to secure cryptography. So it starts with, the discrete log problem is a mathematical problem that is yet to be solved. It is the foundation of public key cryptography, which allows people to send information over insecure channels without worry that it could be decrypted. In the simplest sense, it allows us to produce one-way calculations, a calculation where if A times B equals C, you can only find A or B if you know them. For example, if you have A and C, you couldn't do the algebra to divide them and eventually find B. So that's interesting. It prevents us from doing that form of division. This problem arises when you apply finite field math to elliptic curves. Finite field math is kind of a complex term, and really a simple explanation of it is that it uses operations such as addition, subtraction, multiplication, and division in a way different from normal math. It is different in that it works more like a clock, with the maximum being 12 hours, and if you exceed this amount, you start again at 1. For example, if it is 10 a.m. and you had 15 hours, you cycle around the clock until you end up at 1 a.m. This is why it's called finite field math. A clock operates in a finite, limited field of 12 hours. What this means is that addition, subtraction, multiplication, and division produce different answers than the arithmetic math that we're used to. Continuing with the example of a clock, 12 is the maximum value in the field. So if we apply multiplication and we say 4 times 4, which normally equals 16, but the maximum of the field is 12, then the amount over 12, the remainder, is what the value is. 16 minus 12 equals 4. The remainder, 4, is your answer. And thus, in finite field math, with a maximum of 12, 4 times 4 equals 4. That's important to understand. Another thing is elliptic curves. And elliptic curves are a type of graph that allows you to do point addition. And this means that every time you add 2 points on an elliptic curve, you will always get a third point. Further, it is a completely symmetrical graph, which means you can take your third point and find its reflection on the other side of the graph. So below you can see the point of addition of A plus B equals C. This also applies to multiplication, using an integer and a point. What cryptographers realize is that if you multiply a point and integer using finite field math, you can produce random outputs with a standardized method. Meaning, if we know the integer and point, we can multiply them and produce a solution. But what if we only have the point and the solution? Well, we could simply use algebra and divide the solution by the point to get the integer, right? The answer is yes and no. If the order, meaning the order maximum number like 12 for a clock, is a prime number, then certain theorems can be used to divide efficiently. However, theorems can become increasingly less able to divide numbers as the order gets larger, because computers solve division of these numbers through trial and error. If you can find a large enough prime number, the only option is to let a computer randomly try inputs until it finds a desired answer.
That was a mouthful and a lot of information. We're going to do a quick review, and I'll add some context as to what this actually means in relation to Bitcoin. Basically, Bitcoin, and cryptography in general, uses finite field math, like the discrete log problem, and elliptical curve scalar multiplication, to define an enormous universe of numbers within the finite field. Bitcoin does this by using a specific elliptic curve with equation y squared equals x cubed plus 7, using an order number modulo p, where p is the giant prime number, 2 to the 256, minus a few numbers to ensure it's a prime. This curve is generated from a set of coordinates g, so that any random integer, or whole number, can be multiplied to g to produce q, another set of coordinates on the elliptic curve. So what the heck are all these variables and coordinates, and why should I care? Well, now that you've got a basic premise as to what finite field math is, you can look at the equation kg equals q, and know that when you make a new Bitcoin wallet, it uses a randomly generated large integer, k, your private key, to multiply with g, the generator coordinates, so that it gives you q, your public key, which are another set of coordinates on the elliptic curve. So I'll say that again. Your private key multiplied to the generator coordinates of Bitcoin's elliptic curve equals your public key. We all know that in Bitcoin, you can share your public key with anyone. Exposing this information only allows that person to be able to see your wallet balance and send you Bitcoin, but they can't access your funds. This is because of the discrete log problem. If you know the public key, q, and the generator coordinates, g, then there's no way to divide q by g to get k, your private key, without simply making guesses as to what k is. So forgive me for the repetition, but I had Eric review the basics again. Let's get back to the video.
If that order is a really high prime number, now the amount of guesses that we have to make to try to figure out what the remainder is within that formula is so massive that it's impossible to do. A lot of very large computers and mathematicians work on the problem of finding really large prime numbers, which is hard to do, so that we can get more security. The larger the prime number, the more security effectively you have from using it mathematically. We're just creating the ability to hide within large numbers, and we want that universe to be as large as it can be. So if you choose a large enough prime number, division is practically impossible to do when attempting to reverse point multiplication. And this is the discrete log problem and is the basis of modern cryptography. Mathematicians currently have no way of dividing these numbers. They can only use computers to guess what number was multiplied by the known point to get the answer. This makes multiplication problems over large, prime, finite fields practically impossible to reverse through division. Much of modern cryptography rests on this unsolvable problem. If it is solved, most of our cryptographic systems will crumble. Computers could theoretically become fast enough to guess solutions through iteration, for example, through things like quantum computing. However, this is very unlikely. To give you perspective on this, the prime number used by Bitcoin is 2 to the 256, or 10 to the 77th. The estimated number of atoms in the universe is 10 to the 80th. So, and this is from Jimmy Song's book, I got this. A trillion computers doing a trillion computations every trillionth of a second for a trillion years is still less than 10 to the 56 computations. If computers are ever able to use brute force to arrive at the solution, then we'll be able to find much larger prime numbers as well as a result. If we reach this stage, Bitcoin's failure would also be the least of our problems. So that section I wrote, and I spent a lot of time trying to figure out how to write that well. I wrote that because I think it's very fundamental for us to understand just how secure these systems really are. And it gives you a lot of perspective on some of the problems and the threats of Bitcoin. When people talk about quantum computing or people talk about at a technological level how it's insecure and Bitcoin can be hacked. Having that kind of an understanding really helps you defend the security of cryptography and thus the security of Bitcoin in a lot of ways.
Please bear with us for a quick message from our sponsors. These videos take a lot of time to make, and we've partnered with brands we trust like Stampseed and the Orange Pill app in order to get the funding we need to bring you these videos every week. Don't store your Bitcoin in cold storage without stamping your seed phrase on an indestructible titanium plate. Stampseed is fireproof, rust-proof, impact-proof, and easy to hide. It has no loose parts and will give you ultimate peace of mind that your Bitcoin is safe and sound for the long term. Click the link in the description below for 15% off your stamping kit. When I finally got Bitcoin, it hit me like a lightning bolt. It was the currency of the future, the only money that truly mattered. But there was a problem. I didn't know anyone else that thought like me. That is until I discovered the Orange Pill app. Suddenly, I was connected with a network of like-minded Bitcoin enthusiasts, right in my own city. The Orange Pill app is more than just a social network. It's a community of passionate individuals determined to change the world, one Satoshi at a time. This series is brought to you by Swan and created by Bit Intelligence. Remember to like this video and subscribe to both our channels for more videos like this every week. Thanks for watching.
So I think another really important aspect of Bitcoin to understand is how the mining process works at a technical level, because that shows you how miners are incentivized to behave as well as how secure the network is. So I have a section in one of the later chapters called the mining process, and it starts with the system created an elegant way to protect the network from bad actors, not just through technology, but through game theory incentives as well. For a new block to be mined and included in the blockchain, a mining node must solve the proof-of-work computational puzzle. The proof-of-work algorithm is solved by generating a hash of the block header items that fall below the difficulty target. Because a hash function's output is random, the only way to produce a low enough number is by guessing. The nonce is the random number that the miners are guessing. So you have all of these other variables that are existing in Bitcoin's memory pool, and are all these transactions that are to be put into the blockchain. And the last thing is like, okay, in order for us to get into the blockchain, we need to meet the difficulty target. And that means this header hash needs to have this amount of zeros pop up in it. Otherwise, it won't be accepted into the Bitcoin blockchain. It'll be rejected.
Okay, another quick review here. Basically, miners connect their mining hardware to the Bitcoin network to receive the latest block header and other relevant data, including the current difficulty target. The information included in the block header hash is the latest Bitcoin version, the previous block hash, the Merkle root, the latest timestamp, the difficulty target, and the nonce. 3 of these fields are pretty self-explanatory: the latest version, the last block header hash, and the timestamp. The Merkle root is basically a nested hash of all the transactions in a block waiting to be mined. The difficulty target is a low number that gets lower as the hash rate rises, effectively making it harder to mine a block. For example, let's say the difficulty target is this. Notice how there are 19 zeros in front of this hexadecimal formatted number. The only field that miners are able to change is the nonce field, which stands for number used once. They modified the nonce value in an attempt to find a hash that meets the difficulty target with the same number of zeros. Miners around the world are independently and simultaneously trying different nonce values and recalculating the hash for the block header. When a miner successfully finds a nonce that produces a hash lower than the difficulty target, they have solved the block and can broadcast it to the network. Other nodes will then verify the new block and its transactions, checking the Merkle root and confirming that the hash meets the required target. Once the new block is accepted by the network, the miner receives a block reward and any transaction fees from the transactions included in the block.
It's a mechanism that uses math to force all of these miners to spend a lot of energy to produce these guesses, because these guesses are produced by computers that require a ton of energy. And the intention of that is to create a high economic cost in order to put any sort of information into the blockchain. And that's the only way that we can prevent it from having any sort of attack. Adam Back in the white paper is referenced for hash cache, which is a similar concept where if we associate a cost with sending an email, then that creates an economic cost and reduces the amount of spam that would exist within a system. So we're applying like the same type of concept here by creating a really large economic cost and using math to force people to do that.
I hope your eyes have been opened to why it's absolutely essential for Bitcoin to use large amounts of electricity to add any new information to a block. This incentive shift is what has pushed Bitcoin miners to find cheaper and cheaper electricity. It's so they can make as many nonce guesses as possible at the lowest cost possible. So how does this affect the real world? Because right now we're just talking about a digital algorithm running. Because of proof of work, the math that secures the Bitcoin network, we have an aggressive eater of electricity that can monetize otherwise wasted energy and stabilize variable renewable loads on our electric grid. So if you want to learn more about why Bitcoin's energy use in the real world is profoundly good for humanity, then you should probably watch this next video here. And don't forget to hit that subscribe button and stay tuned for more episodes like this every week. Thanks for watching.